Now, I don't exactly know why somebody would do this. I mean, it's better than eating Tide Pods, to be sure, but I am kind of glad that he did do this because it allows me to talk about chemistry. Now, we're going to talk about LeChatelier's principle, and LeChatelier's principle can actually look like an escalator, or we can use an escalator to help us understand LeChatelier's principle. Let's take this person here. Also on an escalator, they're not moving quite as fast as the first person, and if you look closely, they do start to work their way down a little bit because the escalator is moving a little bit faster than they are, so their bodies are moving down faster than their bodies are moving up. This one, on the other hand, the person is actually really putting some effort into it, and they are making progress. So they are moving up faster than the escalator is moving them down. And that brings us back to LeChatelier's principle. Now, LeChatelier was a French chemist before escalators were invented. Maybe, I just made that up, but he was around quite a long time ago. He did not talk about escalators. Maybe it was before people tried to go up the down escalator, I don't really know. But in his words, his principle, LeChatelier's principle, is that when a system is at equilibrium, if it gets disturbed by some change, then the system is going to go back to equilibrium. It's going to try to undo the change. It's going to try to oppose the change. So if you heat it up, it wants to cool down. If you add something, it wants to get rid of it. If you take something away, it wants to replace it. If you squeeze it, it's going to try and fill that space with less effort. So those are the main things that we're going to be dealing with. So if we go back to what we know about equilibrium already, we have our equilibrium expression where our products are on top, our reactants are on the bottom, their balancing numbers become coefficients. And equilibrium, as we said before, is a rate. Rate of forward reaction is balanced by the rate of reverse reaction. If I mess with that, I'm going to change one of those rates. That's really what it comes down to. Although for us, it's not going to be talking about rates as much as what actually happens. What is the net result? We know that the rate is influenced by changes in concentration, by changes in temperature, by a bunch of other things. So we know what can influence rate of reaction. Those, in a lot of cases, are going to be the things that influence our equilibrium as well. And you've probably noticed already that when we're doing these things that K comes attached to a temperature. So because K is based on rates of reaction, which means it's also based on temperature. Okay, so what happens if I change the concentration? Well, if I look at this reaction here, if I add more of a reactant, I could also add more of a product, but we'll get to that another time. If I add more of a reactant, well, now I've got more carbon dioxide molecules that are able to react. So the reaction of carbon dioxide producing products is going to be more because I increase the concentration of that reactant. If I increase the concentration, I am going to increase the rate of reaction. So then the concentration of products will then increase because I'm using that increased reactant to make more products. This way. Okay, now for us, what's important is that the amount of, if I've added more reactant, then the equilibrium is going to respond by decreasing that reactant, using the thing that we were just discussing. So the important part there is if I add something, it's going to try and get rid of it. It's going to try and use it in the reaction. And now the language I'm going to use is going to shift toward the products. Add more reactant, I'm going to increase the amount of products. The whole equilibrium is going to shift toward the products, more products. And that is true whether I add more reactant or add, if I do something else, but if I increase the reactant, shift toward the product. When it does that, it is going to reestablish equilibrium. The concentrations will be different because I've changed concentrations, but the K value will be the same because it's an equilibrium constant at the conditions of temperature and pressure and so on. Okay, if I increase the concentration, equilibrium is going to shift to absorb or consume some of that addition. If I add more reactants, it's going to shift toward the products. If I add more products, it's going to shift toward the reactants. Too simple. If I decrease the concentration, well, the opposite. If I take something away, it's going to try and replace it. So it's going to shift to replace some of what was lost. I thought I had more, but we don't. Okay, let's change temperature. Well, if I change temperature, it's going to depend on whether or not it's an exothermic reaction as written or an endothermic reaction as written. If I have an exothermic reaction where heat is produced, and it's been a while, but that means that delta H is a negative value, heat comes out, then think of it this way. If I mess with that heat energy term, well, I'm going to either have to replace it or get rid of some. So in an endothermic reaction, heat is on the reactant side. Please don't ever say that heat is a reactant, because heat is energy. It's not a thing. It's not a chemical. It doesn't have a chemical formula. So it's on the reactant side. It's on the left if you want, but it's not a reactant, because a reactant has a meaning to it. Okay. If the system is cooled down, it's going to try and warm itself up. So if I take some heat energy away from either of those, it's going to shift to get the energy back. So the exothermic reaction will shift toward the products, because I've lost some of the things on the product, some of the energy on the product side. If in an endothermic reaction, the energy is on the reactant side. So if I take some of that energy away, then it's going to shift back toward the reactants. Okay. Opposite is true if I heat it up. Now don't get too worried about trying to memorize, oh, exothermic does this, endothermic does that. You're much better off understanding the reaction. Reactants, heat, products, reactants, products, heat. And then thinking about what's going to happen with that heat and how the reaction is going to respond, how the equilibrium will respond. Okay. So in summary, if I add energy, then it's going to shift to absorb energy, and then that's going to mean something for an exothermic reaction and an endothermic reaction. But honestly, look at the reaction, understand the reaction. If I take energy away, decrease the temperature, it's going to try and warm itself back up. It's going to replace that energy. And true thing for exothermic reaction and an endothermic reaction. But again, understand the reaction rather than trying to memorize those four statements, because you'll get confused at some point. If I change the volume, well, changing the volume of a liquid, a solution, isn't really going to do much good to us. But if I change the volume of a gas, changing the volume of a gas is also going to change the concentration of the gas. So if I make the volume bigger, not just the volume of the container bigger, now the same number of particles are floating around in a much larger space, the concentration has gone down. So volume is connected to the number of moles. Then what's going to happen is that's going to affect the concentration. So if I take a situation like this, where I've got gas reacting with producing a gas, I have a total of 4 moles of gas on the reactant side and 2 moles of gas on the product side. Okay? Because it doesn't matter that one is nitrogen, 3 of them are hydrogen, 4 moles of gas in total. So if I have a bigger volume, then it's going to shift to the side that can fill that volume. So more volume on the previous one means 4 moles of gas fills the space better than 2 moles of gas. If I decrease the volume, well, 2 moles of gas fits better than 4 moles of gas. And it comes down to the number of moles of gas. Now, you'll notice moles of gas is highlighted because it's not the total number of moles. If you are looking at counting up solids or liquids or aqueous, you're missing it, because only gases apply pressure. Like that. Okay, what about a catalyst? Well, what does a catalyst do? Well, I know a catalyst is going to make the reaction go faster, but the catalyst is not going to change the equilibrium concentrations. It'll get to the equilibrium faster, but it's not going to be different concentrations. So catalyst is really going to have no effect on an equilibrium. So LeChatelier's principle, if you have a catalyst being tossed in there, it's not going to do anything. It will make the forward reaction and the reverse reaction both equally faster and have no influence on the concentrations at equilibrium. So if I take a system at equilibrium and then throw in a catalyst, nothing happens. Okay? No effect. What if I add an inert gas? Without going into the whole details, it's going to increase the pressure, but it's not going to change concentrations. It's just going to get in the way. So because it interferes with the reactions that are supposed to be happening either direction, then it's just going to be, nothing is going to happen. So there's going to be no effect on equilibrium. Okay, we're going to take a look at this one in class. We'll show you this one, but what I'm going to get you to do is make some predictions. So taking a look at this system at equilibrium, what happens if I were to add water? What's it going to shift? What happens if I add hydrogen chloride? Which direction will it shift? Or sodium chloride? Or silver nitrate as a solution. Okay, and then we could add, don't have enough information on there, but we'll also look at what happens if I change the temperature. Okay, so in summary, by the way, there's not a lot of math. There's no math in LeChatelier's principle. It just comes down to a qualitative, this is the direction it's going to shift. Understand too that when I say shift to the products or shift to the reactants, this is what it means. Okay, so that's what we worked with today, and then we'll get some practice with this in class, and we'll talk to you another time.